this lecture. Now, our arrays and string lecture here is going to be very short because we basically did arrays and strings in year 1 programming. So it's not really much that we need to go back through, but however, there's going to be a new concept here that you're actually going to have to do a little bit of work on. So we're going to be watching why do we need to use arrays and strings in particular for any further advanced data structures. And any sort of questions that you get with arrays and strings, they are going to be interchangeable because a string is basically an array of characters. So any sort of array question that you can get can also be applied to string questions. So just keep that in mind because both of them are basically arrays. There's just different data types regarding the array. So if it's a string, that means the data type of the array is going to be characters. If it is that it's an integer array, that just means the data type of the array is going to be integers and so forth, regardless. But the operations are basically going to be the same no matter what, because they're just arrays. Now, one particular data structure that you will encounter regarding arrays and strings is going to end up being a hash table. And what this does here, it does a nice mapping for us to make a fancy lookup table using a key. And we're going to focus on a very simple implementation using this. So in our simple implementation of using this, we use a linked list, which you also did in year 1 programming, and we map this linked list to a hash code in order to get our hash table accordingly. So the key, which is going to be our search index, is basically that we need to formulate what this key is going to be by making a hash code. And we map that hash code there to an index in the array, being the value that we wish to map it to. And at that index, we have some sort of linked list of keys or values. And we store the key and value for this particular index to go about doing this lookup table accordingly. Now, the reason why we end up using the linked list here is that we need to make sure that we don't have any sort of data collisions, meaning that we don't want such that if we look for a particular key, we end up getting multiple values, or if we have any sort of conflicting data that's coming back, we try to prevent that because those are what we refer to as collisions. So it may be possible that we have 2 different keys to the same hash code, but in some cases we may not want this. And then we may also have 2 different hash codes to the same index. And again, in some cases we may not want this because we end up getting multiple values. We may end up having a one-to-one mapping or a one-to-many mapping that determines on the operation of the hash table. The retrieval basically means that if we try to look up the value using that key, is that we do the same process where we get back the hash code and we get the index and we go through the linked list to find that index match. Now, if there are a lot of collisions, meaning that if there's going to be multiple data being sent back for any lookup value that we try to find for, the worst case runtime of this is going to be O of n, where n is the total number of keys that we have to look forward. If there are minimum collisions, that means using a hash table is very efficient such that we can get the order going down to O of 1. So a nice idea of this is by this illustration here. Let's say if we have to find the value high here, we can translate high here into some key using some sort of mathematical transformation, and then we can map this key here to the index in the linked list here, which will actually store this value of high accordingly. Similarly, if we have some value ABC here, we can also get this hash code here from a mathematical transformation. And if we know at node 0, this also stores the value of ABC, we do this mapping again to node 0 in our linked list to go about finding and retrieving this value. The same things can be done here as well to get our values. As of such, it's just basically like a fairly fancy mapping to go about retrieving these values using some lookup value here. So if I annotate this, So if I draw a line here, this would be values to find. These will be computed hash keys. This here would be our linked list index. And these here would be values to be found. So we establish a mapping using the computed hash keys to our linked list index here to go about finding these values in a faster manner. Now, we will see how we can go about implementing a hash table using something referred to as a balanced binary search tree. And that's like really later on, coming down to the end of our lectures, we'll actually see this concept. And in that particular case, we get our lookup time, and being our worst case, or our average case, going down to O log of n. Hash tables are computationally efficient in terms of time and space, because the time means it's a lot less time for you to search for something, and it uses a lot less space because we no longer have to allocate one set of memory to do these lookups. It's a lot more efficient because it uses less memories to do this mapping. And your lookup keys can be iterated in order if you're trying to find a match, which actually can be very useful because if we sort the keys from lowest value to highest value and we input our search key, we can then optimize that searching even faster to get about even faster lookup time accordingly. Now, I know the hash table concept may be a little bit complicated, but a nice way to think about it is that, if we go back to our illustration here, is that we just basically need to get some computed value here to look up, to match our index, to find our search values here to the values where they are going to be stored and so forth. It's just basically a fancy lookup table. That's all it is. Now, for dynamic and resizable arrays, you already have some experience with a resizable array and a dynamic array here, which is basically your strings that you have been using. The strings basically are resizable and dynamic character arrays. Another example of a resizable array, which is more popular, is also known as the vector. And as you append items, or you delete items, these arrays grow and contract accordingly. And we saw an example of this in the space and time complexity lectures that we did last week. So, if you need to have an idea how this expansion and contraction works, go back in the space and time complexity lecture to see how actually we went through in detail as to how this works with regards to space and time complexity. The string building, this comes like if we're going to be like joining one set of strings together. We need to figure out what's going to be the runtime for joining all these strings together as such. So our assumption is that all the strings have the same length. We say that length is denoted as x here. And the number of strings that we need to join is going to be n. So what happens when we try to join two strings correctly is that we copy the original string first and copy the next string, and this is done character by character. And for the first iteration, we copy x characters, and the second iteration we copy 2x, the third iteration 3x, and so forth, as we keep on going for each concatenation. And then that means it will end up being O of x plus 2x plus 3x all the way up to nx. And if we use our arithmetic progression formula, this is reduced to O of x n squared. So this is the sum of integers formula because we had 1x, 2x, 3x, 4x all the way up to nx. So the same techniques that we use for space and time complexity and the same assumptions and say mathematical notations can be applied to find the space and time complexity of any one. So that's why you need to go back and review what happens when we expand a dynamic array in our space and time complexity lecture. C++ uses something referred to as mutable strings, and these are the nicer form of strings that you do want to use because it avoids a lot of problems. If you were using something referred to as immutable strings, there are a lot of problems associated with them, and it tends to be a little bit complicated to use because then you'll have to end up using something referred to as a string builder. So depending on the type of programming language that you end up using, you have to figure out if strings are going to be mutable or immutable to figure out how do you work your way around them. So, I'm assigning you guys some homework here. In C++, hash tables do not really have their own library or class. There's a sort of workaround to using them. So your homework is actually to figure out how hash tables can be used in C++, and I'm giving you a starting point here. You will actually have to look at how unordered maps work accordingly. And because depending on your mini project, you may end up using different programming languages, it's advisable that you actually look up what's going to be the difference between mutable and immutable strings, because this may actually apply to the programming language that you may end up using for your mini project. Same time when you're looking up mutable and immutable strings, you can also check why C++ ended up using mutable strings instead of immutable strings. So that's the things that you're going to have to pay attention to regarding this. Now, just to reiterate the points here from this lecture, the hash table concept is basically a fancy lookup table, which is actually very important for using search functions in particular. And a hash table is a very optimized way of getting your searches done very fast, as well as using the least amount of space possible for storing your indexes and your retrieval values regarding your search database. In order to go about seeing how we implement these in C++, there's no defined class or functionality for hash tables, but there is a workaround function known as an unordered map. So you're going to have to do a little bit of research regarding this. And depending on the programming language that you're using, you're going to have to search up if it's going to be mutable or immutable strings, and you're going to have to see what's going to be the differences between the two. Alright, so question here. Yes, you will be writing C++ code in terms of the quiz. So you will have some theory-based questions, yes, but there will be parts of the questions in the quiz that you will have to end up writing C++ code. There will also be parts of the questions where you may have to write C++ code, but in your comments you're also going to have to put your details as to how you went about writing this code and why you made certain decisions writing these. What I can tell you so far is that the only thing code-wise that we did look up was basically your code review for operations and basically code analysis. Those are the only things that we actually went back. And I believe the other thing code-wise that we also watched was classes and or recursion and dynamic programming. So those things you might want to pay a little bit of attention to. Alright, that brings us to the end of our second lecture for today. Any particular questions? Alright, doesn't seem like we have any particular questions. Right, so let's end this arrays and string lectures, and let's get on to our first sorting and searching algorithms lecture here. And if we manage to finish this in particular, that means if we finish this today, that we can go about any sort of review on Wednesday, in particular regarding any particular topics, once you get your information on the quiz. So we can focus on that instead of going through this lecture on Wednesday instead. So let's go on to sorting and searching algorithms, yeah? Hold on.